Hello. So today we're going to be going over the flashlight problem. Basically, this is a problem where we have four surfaces, and when they are put together, they create the shape of a flashlight in a graphing program or the assumed shape of a smooth flashlight. Specifically, we are going to be working on using Stokes' theorem to compute the flux of the curl of the vector over the surface. And then later on in this video, we are going to be talking about using Gauss's divergence theorem to compute the flux of the vector field over the surface S. We are additionally going to discuss why we can use these theorems. Let's get into it. So beginning with Stokes' theorem, we are going to be assuming that our vector field F is equal to yz in the I direction plus x in the j direction plus e to the x squared minus y to the 17/4 plus arctangent of xz squared in the k direction. Now I have a little passage up on the screen about how that would be computed directly, which is a part of my honors project, which is also linked in my portfolio. But specifically, we're going to be talking about using Stokes' theorem and why we can use Stokes' theorem. So Stokes' theorem allows us to compute the flux of the curl of the vector field over the flashlight as instead of computing that whole, all four surfaces individually, we can compute it as the line integral over the boundary of the flashlight. Now, Stokes' theorem applies because we have a piecewise smooth curve, and we can therefore use Stokes' theorem and compute using only the line integral. Now, in order to use Stokes' theorem, we also need to parameterize our function, and we are specifically looking at what is considered the boundary of the function. So that is going to be the same thing as the boundary of section 1, because section 1 represents the base of our flashlight, and everything after that, or above that, I should say, stacks on top of that and is a piecewise smooth curve. So we're going to parameterize section 1. Section 1 is x squared plus y squared equals 4 squared, which is a circle with a radius of 4. Now, S1 is a cylinder between -1 in the z direction and +1 in the z direction. Now, if we parameterize this as r cosine theta, r sine theta, and then the value of z, we end up with 4 cosine t, we are using t instead of theta, comma 4 sine t, and -1, because -1 is our z value at the very bottom of the flashlight, or the base. So using this as r of t, we next need to find r prime of t. R prime of t is the derivative in each direction. So the derivative of 4 cosine t is equal to -4 sine t, and that's for the I component. The derivative of 4 sine t for the j component is 4 cosine t. And the derivative of -1 for the k component is 0, because the derivative of any constant is 0. Now we need to parameterize our original vector field, which we can do so. Now remember, our original vector field is yz, x, e to the x squared minus y to the 17/4 plus arctangent of xz squared, all in the k direction. Now this is going to equal -1 times 4 sine t, which is y times z, which is -4 sine t, x in the j direction, which is simply 4 cosine t, as we see here. In the k direction, this becomes e to the x squared, which is going to be 4 cosine t squared, which is 16 cosine t squared, minus y to the 17/4, which is 4 sine t to the 17/4, plus arctangent of 4 cosine t, as we have arctangent of xz squared, and -1 squared is +1. Now we are going to integrate the dot product of our parameterized vector field and our parameter, the derivative of our parameter, with respect to dt. This is our line integral according to Stokes' theorem. So again, remember we are using t and t is going in a circle, which means t is going to go from 0 to 2 pi, as theta would. Now, when we take the dot product of these two, because the third term is 0 in r prime of t, the final and very long term in the k term is going to all cancel out into 0, if that will properly highlight, which it will not. Okay. So as we can see, we have negative 4 sine t times negative 4 sine t again, plus 4 cosine t times 4 cosine t again, all under dt. This is the same thing as 16 factored out of sine squared t plus cosine squared t. Now sine squared t plus cosine squared t is a trig identity, and that adds up to 1. So here we have 16 times 1 dt, which we also have represented over here. This can be evaluated as 16t, where t is evaluated from 0 to 2 pi. If we factor out the 16, we have 16 times 2 pi minus 0, which is the same thing as 16 times 2 pi, which is 32 pi. Now we are going to use the divergence theorem, which is Gauss's divergence theorem, to compute the flux of the vector field over the surface S, which is our flashlight. Now, for this, we are assuming that our new vector field is negative y to the 7/4 plus x to the 21st in the j direction, plus 5z in the k direction. Here we have stated Gauss's theorem. Gauss's theorem relates the flux over a surface to the divergence over the volume. This can be an important step in simplifying our problems. So, in order to use Gauss's theorem, we must meet a certain requirements. These requirements are that S must be, our surface, must be a piecewise smooth closed curve that encloses our solid in space. Now, we have a piecewise smooth curve, but it is not closed. This is because we have an opening where our flashlight would light up or where the bulb would be. This opening is in the shape of a circle with a radius of 4 where z is equal to negative 1. Thus, we can close our surface by adding a circle with the equation x squared plus y squared is less than or equal to 4 squared and positioning it at z is equal to negative 1. Now, in order to use this, we are going to need to subtract it from the left-hand side. This is because our flux over the surface, that whole surface does not include our circle, because our circle is not a part of our original shape. Additionally, it's important to note that the divergence is calculated by taking the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. And this is going to be equal to, since we have our vector field here, and we have no x terms in the I direction, and no y terms in the j direction, and one z term in the k direction, 0 plus 0 plus the derivative of 5z, which is equal to 5, and that added together would also be equal to 5. Here we have written out the adjustment that we need to make in order for this to be true, as we are subtracting out the secondary flux integral, or in this case, what would be our fifth surface, which closes our region. So in order to use this formula, since we would need to add it to the left-hand side, we can also use it by subtracting it from the right-hand side. Now we are going to solve for the right-hand side. It's also important to note that our requirement is to have outward orientation for our normal vector over S. We do this by establishing a normal vector that is facing outward from our function. This is easiest to complete by using our new circle surface because it lies flat on the xy plane. If we establish it at a starting point of 0, 0, negative 1, then we can use the vector 0, 0, negative 1. This is pointing downwards away from our graph. Now it's time to solve. Here we have the divergence of f, which is going to be the triple integral of 5 dv minus the double integral of our vector field dotted with the normal vector ds. Now, this is going to result in the first two terms being canceled out for our flux integral and the third term being multiplied by -1. The result is -5z dA because we are doing a double integral, which is with respect to area. Now we have a triple integral of 5 dV, which is the same thing as 5 times the volume over our region, minus -5z dA. It's important to note that z is equal to -1 in our region, which closes the graph. This means that we have the triple integral of 5 dV minus the double integral of 5 dA. This is the same thing as saying 5 times the volume of the flashlight minus 5 times the area of our circle, which closes our region. Here I have the volume of the flashlight written out, as well as the volume formula for the circle. We are adding the volume of the first cylinder, the volume of the second cylinder, the volume of the cone, and the volume of the hemisphere, which make up our 4 surfaces in our flashlight. Here we have the volume of the cylinders and the hemisphere plugged in. Note that a hemisphere is 2/3 times the rest of the formula, whereas the volume of a sphere is 4/3 because we are looking at the top half of a sphere, which is our hemisphere. Additionally, we have already solved for the area, 5 times the area of our circle, which the area of our circle is 8 pi, 4 squared being 16 divided by 2 is 8 times pi, and that times 5 is 40 pi. It's also important to note that for the volume of our cone calculations are a bit more complex, as our cone is not an entire cone. It has a hole in it. While it may not directly look like it has a hole in it, what I mean by that is that it's missing its top part. So if we calculate the cone as assuming that it has a top part and then subtract out the upper part of that cone, which does not exist in our formula, or in other words, the volume of the cone minus the volume from the hole to the tip of the cone, we can get the volume of our actual cone. The radius of the whole cone is going to be setting the equation of our cone equal to 1, given our surfaces. Solving, we get that the radius is equal to 4. Solving the radius of the whole is the same thing, only this time we are setting our equation equal to 3 because z equals 3 is the surface that cuts our cone, as we know from up above where we have our 4 surfaces listed. Here we're discussing surface 2, which is the cone cut by the plane z equals 1 and z equals 3. Now that we have set these equal to 1 and 3, and we can solve for them, we get that the radius is equal to 4 for the main cone, and that the radius is equal to 2 for the whole. Now we can plug in our values. Here we have 4 squared, which is 16, times 2, which is 32, times pi. So we have 32 pi. Plus, we have the volume of the cone, which is 1/3 pi r squared, times height. Starting with the radius of our main cone, we have 4 squared. And then we have 4 as a unit of height, because we are assuming that the cone goes from the plane z equals 1 to its vertex point at z equals 5. Then we are subtracting out the volume of our whole cone, which is 1/3 pi times the radius squared, the radius being 2, times the height, which goes from the plane z equals 3 to the vertex point z equals 5, which is 2 units. Then we are adding the volume of our second cylinder, which is 28 pi. Additionally, we are adding the volume of our upper hemisphere, which is 2 to the 3rd power, which is 8, times 2, which is 16, divided by 3, times pi. And again, all of this is being multiplied by 5, and we are subtracting out 40 pi. Now, this seems like a complex number, but when we actually go and do the math, we notice that the volume of our cone ends up being 56/3, And since we're adding that to 16/3, the result is 72 pi, which is divisible by 3 and becomes 24 pi. Now you have 32 pi plus 24 pi plus 28 pi times 5. Then we are subtracting 40 pi from that. The result is 380 pi. And that is how we calculate the flux of the vector field over our surface using the divergence theorem, which makes it a much simpler calculation. Here are some images. Here is the entire cone image. As you can see, the cone goes from the plane z equals 1 to z equals 5. But for our function, we are only using the part from z equals 1 to z equals 3, which is represented by the purple to the gray lines. Here is the part of the cone that we are calculating in green, and the part in blue is the part that's being subtracted out from this entire blue cone, which is what we calculated, and that is the radius of the hole and the height of the hole and overall just the cone of the upper portion. And this is our entire flashlight drawn out, including our parameterized curve and our enclosed surface. Thanks for watching.